So great, so let's get started, everyone. So welcome back. Hopefully you're enjoying being in person and seeing your classmates. But so we have a quiz today, so I want to make sure I get through all the material. So just a couple reminders. The TA office hours have been posted up here. So make sure that so that you can make it to at least one of the TA office hours. So if you can't make it to one of these office hours, please send me a note. There were a couple people who requested specifically Zoom office hours. I'm sure you can. I think we're not going to host Zoom specific ones. Although you can definitely kind of contact me or probably any of the other TAs requesting to be on Zoom during their office hours, and they can set something up. But it's just going to be hard to balance kind of both of those things and find a single Zoom time slot that satisfies everyone who would like the office hours primarily on Zoom. So we'll plan to primarily, the main purpose will be the in-person office hours, but you can request some meetings so Zoom outside that. What I don't want to hear is if you are able to attend stuff in person and you tell me at the end of the semester, oh, I couldn't make it any of the office hours. If you tell me that now, we can still rearrange them. I think we've booked what I think is supposed to be the best room for office hours this semester. I got early in the booking process, so we were able to secure that room. But please tell me about that if that's going to be an issue. A couple other things to point out on the website. A couple things have changed. Okay, so the video link, I capitalized YT, saying for YouTube. That means that I posted a link to the video on YouTube. Okay, so as during the semester, the lowercase will change to capital, and you'll have access to all of these videos. I've also posted the slides that I showed last week. They're open here. You can open them in another tab and go through them. Right, I know for a lot of you, taking notes during the lecture is a good way of learning, and I so encourage you to do that. But the material, everything I write will also be made available so online. So if you didn't write fast enough for something, it'll be available up here. Hopefully, the fact that I'm writing almost everything on the slides means that material is not coming too fast for you to comprehend it and also write it down. Okay, the other things on the schedule, if you see on the right side here, quiz 0 is today. This is going to be a Canvas quiz. It doesn't open until let's see, I think 11:35 today. So 11:45. Great. Okay, so it will open at 11:45. I will if you can confirm that. And we'll try and do it during the lecture. If it's 11:45, I will stop lecturing by then, and then you will have time to take the quiz here. I expect, especially the first quiz, people to finish well ahead of the 30 minutes limits. During the other quizzes, this first one is basically practice, okay? So don't worry too much. It's about the syllabus. You can look at the syllabus or the webpage during the quiz. Okay, I don't want you talking with other people, but you can look up material during the quiz. The other ones, you'll also be able to look at material during the quiz, but if you haven't looked at it until the point where you take the quiz, you aren't going to do well. It's going to take, you're not going to be able to learn all the material in 30 minutes in most cases. So those quizzes should still take far less than the 3 minutes time you're given. So you should expect to finish it. A typical student finishes about 15, maybe 15 to 20 minutes. a number of you will finish much, so less time than that. And then homework 1 will be posted by next Tuesday. So that's what it means to be in that line on there. Hopefully before next Tuesday, we'll have this posted in the next class. All right, so any questions on the schedule?
Yes, you mentioned the 30 minutes. I thought it was open all day.
So you have, once you start it, you have 30 minutes to finish, and it becomes available at 11:45. Okay, and it closes before midnight. Okay, so you can take it at any point, but once you start, you have 30 minutes to finish it. Okay, I don't make it open before then because I don't want you to take it during the lecture, right? So, so after I'm done lecturing, it'll be available, and I encourage you to so to take it here in class. If there are questions, you can ask me questions. All right, but it'll be a quiet place here to take it. So great. So today, also I want to look at just the schedule. The next couple of lectures, this one included, will be mostly a review of probability. If you've taken a probability class before, I'm going to try and cover most of that class in so 2 lectures. It's not all of the class. Clearly, I can't cover everything, but I'm going to try and review the notation and language that was needed that we'll be using so later on the semester. I will be moving through this material more quickly than I will the other material, because for many of you, this is going to be a review. So don't be kind of alarmed if I move through it more quickly than you're used to seeing this material. When we get to the newer material, I will, of course, move more slowly through it, more examples, more dwelling on kind of different aspects of this. Okay, by the following week's set of lectures, the ones on the we'll start with so Bayes rule. Hopefully you've seen Bayes rule before, but we'll use it to do some cool stuff. We'll actually derive, and you'll see some really cool ways of turning how to drive an estimator from Bayes rule and data, right? So by this lecture, you'll probably start seeing some new kind of cool things you haven't seen before. These lectures on convergence are also kind of an extension of probability. These will be how we think of kind of using probability to analyze how well an algorithm is working. If you have a probabilistic algorithm or an algorithm that assumes randomness on the data, how do you describe how well this is actually working? That's what we're describing in these lectures. And then we'll kind of switch to linear algebra as our language and then start describing these algorithms. And this will give us the language to think about how well they work when there's randomness involved here. All right, so that's just kind of a preview. All right, so let's, so on to the lecture. Oh, so I also mentioned that there's all this boilerplate in the syllabus that we are required to have in the syllabus of all the classes. We're required to go over it on the first day. You probably saw it from everyone. Probably all the instructors go through it very quickly. I wanted to kind of go and bring each of these up because I think they're actually kind of important points. The one I wanted to mention today is that there is support for students who have either have different styles or abilities of learning or come from different backgrounds. With the Center for Disability Services is quite broad. I expect in a class this size, I'll have about 5 students who approach me. So don't feel ashamed if you have to do this. See, baby knows I have a stutter. This probably won't influence, so much my ability to learn. But like other people who have kind of different ways of learning, they have a lot of options. Okay, and I will work with you to accommodate those things. other people. Maybe English isn't your first language. Some of the best students that I have in this class, English has not been their first language. There are resources on campus, and if it becomes an issue, I'm happy to work with you in that case. Okay, great. So let's get into the lecture. All right. So I'm going to kind of define the notions of probability that you need, and we're going to approach this. There are lots of levels you can define probability. There's one from measure theory. We're not going to get into measure theory. I might mention that the definition requires that a couple times. There's also a version of trying to describe all probability you'll see in classes that does not rely on calculus at all and does not assume a knowledge of calculus. The class you've taken, CS 3130 or Math 20 or Math 3170 is a calculus-based version of calculus. But for instance, the one taught through the psychology department, I think, is not one based on calculus. We're going to be on this like middle ground. We won't need a lot of calculus in this class, but the knowledge from it will be kind of essential to understand at a few places. But we're going to start by talking about something as simple as sample spaces. Okay, and we're going to define this through a Greek letter. This is omega. Okay, and we'll think of this as a space of all possible things that can happen. Okay, so it's not everything that can happen, but when we're talking about probability, we need to somehow focus our attention to some space of events, right? So if you're going to get a grade in this class, the university only gives me a discrete set of grades that you can get. If you're going to get a numerical value, right, then it's going to be between 0 and 100. Actually, there might be a little bit of extra credit possible, so maybe between 0 and 101.5 or, so something like that. But there's this fixed region of events that can happen, and that's what we're going to study, focus our probability on the space. And so I like to think of things geometrically, and so I'm going to draw a picture. This rectangular box is going to be the sample space. Okay, and this is the space of all possible events. Okay, we're then going to consider some other things within this. We're going to say, lowercase omega is going to be something that's in the sample space. This would be a called sample outcome. Okay, this is something that could happen, right? So something that could happen would be a point in the space. Okay, so a point in the space would be something that could happen. If you got an A in this class, that's something that could happen. If you earned a 91.2%, that's something that could happen in the class, right? That would be a sample outcome. This notation, right? So we're going to be talking about kind of the mathematical notation for kind of data analysis. This notation, you have a set, you have an in operator. It's saying that omega is something that's in the space, right? So I could not choose something out here. This one this one would be not in. So this way I would write, this is not in the space because it's outside there, right? So that's what this notation means. We're going to use the notation throughout the class, right? I will try and remind you if I use a notation that I think you may not have seen before. I'll try and tell you what it is. If I use one you haven't seen before, raise your hand and ask me about it, and I'll explain it. This is important. If you haven't seen it before, probably a lot of other people haven't. Understanding, like one of the goals of this class is so that you guys can understand kind of machine learning, sort of some literature, whether it's on Wikipedia or a research paper after the class. And it's written using this language. So you kind of need to know what these symbols mean. I'm not just making them up. And they actually are very useful. they're allowed us to describe things very concisely in a way that will actually help the understanding. Yeah.
Is omega the usual symbol for sample spaces, or because I know I just use A or B usually?
Yeah, I will try and, yeah, we'll typically use omega for sample spaces. I'll use A and B for events, which will come next. So I've tried to choose things that are common and I can use fairly consistently throughout the class, but that won't always, there are only so many letters. But I mean, there are certain letters that you don't like to use because they look like other letters. There are only so many kind of good letters in the class. So, so in the probability section, we will, another thing we'll think about is going to be an A, which will be a subset of so omega. This is going to be n. So we're going to call this an event. Okay, now I'm using a subset instead of in. In is usually a little bit smaller and has the little line in it. Subset is going to be not just one object, but is going to be a set of possible objects. All right, so this would be a subset of the sample space. Everything that falls into here, right? Everything in this range is A. Okay, so it involves many of the sample outcomes. The subset from measure theory, or the event needs to be so quantity that I can measure. It has to be so measurable. But we're not going to worry so too much about that. Kind of a more concrete example. I mean, I like to draw pictures of these things. I think that helps me a lot, but kind of a concrete common example would be kind of a sided die, right? So if I roll a die, then the sample space is the outcome is what number comes up on top, 3, 4, 5, 6. It's a set, right? There's elements separated by commas, and there are curly brackets around a set. Okay, if you remember, a set means the order of these things does not matter inside. I just have a bunch of possible outcomes. You can think of these as all the points in here. The points are kind of continuous. The sets are these discrete outcomes. So the sample space, now I roll a die, I could roll a 3. That would be an example. Sample outcome would be 3. And I'll get your question in just a minute. And an event might be, for example, might be 1, 3, and 5. This would be a number which is odd, right? So this would be a subset of the sample space. It could be a subset of size 1, but it's more interesting. Hey, I can think of a subset of 3 possible things. All right, question.
When you know the subsets, do you have any preferences?
Oh, okay, yeah. So this is an interesting question. The reason why is I'm going to encourage you to use LaTeX, right? And in LaTeX it has notation. I would write this in so inside of LaTeX as so I would write so omega. That's a lowercase omega. It looks like a W, but if you look in the textbook, it's a lowercase omega, slash in slash, so then uppercase omega, right? If I write it like this, it will compile into mathematical notation. I don't have keys. I don't have keys on my keyboard that make these symbols, right? But so LaTeX, if you're a computer science major, you programmed before, you're writing code. These are predefined variables. This is lowercase omega slash in. That gives me the in symbol. Uppercase omega gives me this uppercase omega. I can do similarly here. I would just do A, and then I would do so subset, and then so uppercase omega. Okay, so I would prefer that you try and write this using the LaTeX, and then you're going to get it formatted. It's not exactly a C. When I write it on the board, it looks kind of like a C, right? I get that, but when you're writing mathematical notation, you want to actually make sure that it's precise. And if you write a C, it's not going to look quite right. Yeah.
Do you care about the differentiation between proper subset or subset that might be?
Yeah, this could be important. In fact, you are right. This definition, an event might be a subset which includes all of the sample space, right? My event could be I roll the die. It was 1, 2, 3, 4, 5, or 6, right? That could be my event. That's the whole sample space, and it could be an equal. So then it's a non-strict subset, and that would be allowed here. And that would be, I think that would be subset equal, I think is the right command, but you can look these things up. There's lots of resources.
So you want us to make sure that if we're just using the subset, it can't be the entire sample space?
No, it could be the entire sample space, and that's fine.
Okay.
Yeah, in fact, the probability of that we'll see is going to be 1. That will be something that we will define. Yeah. Yep.
Is there a specific way you want us to do with empty set? Like
The empty, it could also be an empty set. Yeah, there's a command for empty set. I'm not going to go through all of these when I see something new and important that I often see people not writing in LaTeX. I might make the note, but I'm not going to define every command in LaTeX in the lecture. Yeah. Right. But yeah, you should look up these. It'll make your writing much more clear, and it's going to look much more professional. Okay. So, if you're writing it on the quiz, if you just write the word subset, that's probably better than using a C. A C, I might not know what you mean. If you write the word subset, even without the LaTeX, that's probably better. Yeah. All right. Okay. One thing about an event is I will be able to talk about the probability of an event, right? So I'll say the probability of A, which is probability of the event A. I'll try and use P sub R here to distinguish from just a P as probability. I can say the probability of an event. We don't quite know how to define a probability yet. I'll see that soon. But if this is a fair die, right? So if each side is equally likely, then this probability is going to be equal to 1/2. Right, so events over sample spaces are what I'll be able to talk about the probability of. Outcomes will be, I can only do that if it's measurable. So if it's a single point, it turns out I won't be able to say something about the probability. And we will get into this distinction a bit in probably a couple lectures. All right, so in general, a probability, okay, is so PR of this event A has the following properties. These are what it needs to satisfy, and then you can come up with how you kind of model that probability in a variety of ways we'll get to. But the properties it needs to have is that the probability of A needs to be between 0 and 1. Okay, so for any probability needs to be between 0 and 1. It could be 0 or 1, but it can't be like, you can't have probability of this happening is 2, right? Right. So you can't say something like, 5/3 of all people don't understand fractions or something like that, right? So the probability needs to be between 0 and 1. If I take the probability of the entire sample space, right, this is why we needed a non-strict version of the subset, this has to equal 1. Okay, the sample space is everything we care about when we're talking about probability. So if I say, well, the probability that it fell somewhere in the sample space, well, that has to always be true, right? So that means the probability is 1. And then there's the law of total probability, and that's that if I have some disjoint events, that's A1 through A2, and these can go on. I don't need to have a bounded number of these, but I need to have that from a set notation. The intersection of any AI and AJ is going to be equal to the empty set, right? So these don't intersect with each other. Then if I write the probability of the union of all of these sets, all right, again, union has a specific kind of way of writing this inside LaTeX. If I take the union of all these, right, so it could fall in any of these different events, right, then this will equal the sum equal 1 of the probability of each of the individual events. Okay, so if I had the example with the die, right, so let's say I have this die and it has 1, 2, 3, 4, 5, and 6, and I have 2 events. The first event A is 1 or 2, and the second event B is 3 or 4, right? So I could say maybe the probability of A equals 1/3, the probability of B equals 1/3. The union of A and B, or A1 and B would be A2 in this case. The union of those would be any event in 1, 2, 3, or 4. Okay, those are disjoint, they don't overlap with each other. So then I know that the probability of A union B is going to equals 2/3. Okay, so that's this law of total probability is the third case here. Okay. Okay, so again, a lot of you have taken probability or might be co-taking probability, and this, if you haven't seen this yet in that class, you'll see it very soon. Right, so another example, so let's say I have bias coin. Yeah, if you turn in a homework and you draw the answers, you write it out by a stylus and it's clear and we can read it, that's totally fine. Some of you have great handwriting and this works out better. It could be on pen and paper and you can scan it too, that's also fine. If we can read it and it's clear, it's fine. If it becomes not legible, the TAs might grade it incorrectly because they can't read it and they have permission to do that. Okay, so, but if it's clear, and some of you will write things very clearly, and you know, so then that's great. Yeah. Okay. So let's say I have a bias coin. Okay, and so the bias coin, it can be heads or tails or heads. Okay, and we can say that there are 2 possible events. A1 is tails, A2 is heads. Let's say the probability of tails is equal 0.4 and the probability of heads equals 0.6. Okay, so this is one of those trick coins that it's not 50-50 what side it lands on. This is still okay. Right, these events, it can't land on heads and tails at the same time. We're ignoring it landing on the edge, something weird like that. And that the sum of these 2 things is 1, right? So these are all the events. The sample space is just heads or tails. Okay, and so I have that the probability of heads plus the probability of tails is equal to 1, right? So this satisfies the law of total probability. Both of those values are between 0 and 1, and the full sample space, the probability of that is equal to 1, right? So this kind of, it aligns with the definition I wrote on the previous page. Okay. You could also have a continuous sample space, okay? Things like heads and tails, rolling of a dice, the grades that you're ultimately letter grades you're assigned in the class, those are discrete possible outcomes. You could also have real outcomes. That could be, for instance, like the numerical grade that you get in the class. Probably no TA is going to assign so like an irrational number of points to something. In fact, probably that's not allowed in Canvas. Okay, but you know, you can imagine it could be a continuous value. So then, if that was the case, I couldn't assign, you know, the probability that someone in the class got 90 plus pi total percentage points, right? That would be, that specific thing might be very, very unlikely, right? But well, yeah, possible we'll stretch to see how if Canvas can put in real, you know, what kind of grades it can put in this year. But like another example is if like if we're measuring rainfall, so okay, the amount of rain that we capture, right? It's not exactly 0.1 inches. It's some continuous value, right? So that there are also these so continuous so sample spaces. Okay, this could be things like the grade percentage. So so rainfall. So if you're measuring things like time, all right. So if so like time, what time did I start this class? I am supposed to start the class at you know, an example. The sample space is I start the class at you know, so I start class at so 10:45. Okay, but 10:45 is not a specific time. That gives me a whole minute to start the class. Usually I'm watching my computer screen, and as soon as it's 10:45, so you know, I try and start talking. But sometimes, like in the beginning of the semester, I'm getting stuff set up. Yesterday, I forgot my laptop and had to run back to my office to get it. And I maybe started class towards the end of 10:45, or I'm kind of getting stuff kind of set up so it's working online. So it's actually, I could think of this as the real sample space of when I started the class is actually 10:45 and 0 so milliseconds, right, up to 10:45 and or actually let's say 10:46, right? But I'll put an open parentheses here, meaning it does not include the endpoint. This endpoint's included. Anything in here would be starting at 10:45, right? So I could, and now I can have something like a, so I could talk about, so an event that I start class between 10:45 and you know, at the start, and 10:45, and so so in 30 seconds, right? So I could say this is an event, and so what's the probability of this event? So the probability of A, I would estimate maybe this is going to be 0.8. Probably, I expect 80% of the time I'm going to be starting the class in the first 30 seconds of 10:45, right? I'm risk averse. I'm probably not going to wait until the second half. Okay, so I can define probability over these continuous values as well. Okay, and so these continuous sample spaces will be really important in understanding so data analysis. We're going to be drawing and talking about things that have continuous values. When I'm measuring something in the world, something like rainfall, or it's its temperature. Often these are rounded, but we want to think about them as potentially being from some continuous space. Our models will allow us to include that in the modeling. Even though the observations might have been rounded, the modeling will be a lot easier if we have these continuous representations. We'll also be thinking about kind of ways of trying to build things like classifiers and regression on these things, and the space of classifiers and regression will also have continuous values. So we'll need to think about these continuous sample spaces and probabilities on these.
I was just gonna ask, this is different than like an infinite space, right?
It could also be an infinite space, right? I could say the time I started the class, you know, it could be any point. Maybe it's outside of this range. It's after 1046. There was traffic or something, right? So I came late, right? And do I put a bound at 1047 or something? I'd probably before 1205 I'll start the class, but it could be infinite, right? Rainfall. Maybe there's something where rain keeps coming down and drying up, and you know so these things could be infinite. To define probability on those is a bit trickier, but you can still do it. Yeah.
For continuous spaces, we can always just make it smaller and smaller until like it becomes completely.
Yeah, you can think of discretizing down until the smallest thing you can actually measure, right? Yeah, there's an interesting argument about whether this is the right way to kind of model it and think about it. Is the world just continuous or discrete at the finest levels? The point is, mathematically, it will actually be easier and simpler and more intuitive to think about the continuous version. And so our goal is to come up with a simple mathematical formulation that describes what we're doing. The continuous things will ultimately be easier to work with. I don't have to worry about how far it's discretized. I can say it's arbitrarily discretized and everything still works.
And also, is that probability just guessing, or is that just
Yeah, this is right. So actually knowing the probability, this is we're not going to get into this in class today.
okay? Thank you.
Yeah, that's an interesting point about, do I actually know this probability here? We will get into this topic a little bit over the next few weeks, but not in class today. These are really deep and fascinating questions that is, you know, some things are beyond the scope of the class, right? So okay, great. I want to get to kind of a really important concept that we're going to need to define a lot of the next steps in probability and in analysis of algorithms is called is called a random variable. Yeah, so random variables are hard to actually define. To define them, you really need to use concepts from measure theory to do it totally properly. And I'm not going to do that. I've actually tried to do that in the past semesters and try and get away with it, and I don't think it was very helpful. So I'm not going to give you the full definition of a random variable. I'm going to give you some intuition and some examples. One of the reasons I struggle with this is there's a common way you might see a definition that skips the measure theory is not going to be complete for what we use it for in this course, because we're going to talk about high dimensional data, and so that kind of that fact is going to make this a little trickier. Okay, but a random variable, and we'll typically use x. You know, it could be y, z. We typically use uppercase letters. Again, these are towards the end of the alphabet for the random variables. Okay, so we'll think about x. It's a random variable. Okay, and the way to think about this is if you're if you're a scientist, you're programming, you're used to the idea of a variable, right? So think of it as a variable in that you've defined inside of your code, right? In the programming that you're doing, but you haven't assigned its outcome yet, right? You've written the code, and so you don't know what the outcome, what the value it's going to take. A random variable can take different values, and I can write code that uses that variable without knowing what the outcome is, what the value is going to be. Okay, and what we're going to think about here is that how the value will be assigned. I actually know how it will be assigned, but it's going to be a random process that is going to be assigning this random variable. Okay, so there's going to be some random process. Okay, and this is whether controlled by the computer. You can have your computer more or less generate some randomness. You can generate random numbers. I'm not going to get into today how it actually does that and how random they actually are, and it's actually pretty good if you do it the right way. This random process is going to have some outcome. Okay, the random process could be so like I have a die and I roll a die, and the outcome is going to be a face of the die, right? Once I have this outcome, I want to assign it some sort of value. Assigned, so value. Okay, so the value might be 1, 2, 3, or 4, right? So I could have roll dice, face of the die, and then the value, typical value might be 1, 2, 3, 4, 5, 6. Okay, so I might assign a value based on the number on the face. I could assign a different value instead. Maybe I assign a value 10 times the number on the face. That would also be fine. Okay, so a random variable allows me to consider random process and consider a value associated with the outcome. Okay, if you see simple definitions, a lot of them will actually say that these outcome has to be real values. Okay, and this will simplify a lot of the discussion on that. And this is often true, but in this class, we're often going to think about some data which is going to be high dimensional. Okay, so we're not just going to value might not just be one real value, but a vector, a high dimensional vector of real values. And because of that, if I just restricted this definition, it's not going to work, right? It's some space that assigns value. It might be multidimensional. It might live in a subset of all the possible multidimensional values it could take. There are other conditions here, and to do this properly, you need some measure theory. We're typically going to either be R or RD. This is D-dimensional real, so vectors, right? This would be a D-dimensional vector. So the outcome could be a D-dimensional vector instead, or some other dimensional vector. We would specify what that dimension is with the random variable. Turns out like everything works very intuitively once you plug some linear algebra into here, and you can deal with high dimensional stuff, right? So we're going to keep this in mind, that our random variables might not just be a scalar value like a double or a float in a computer, but it might be a vector of doubles, or a vector of, it could be integers, right? It could be a vector of integers, right? These are the possible outcomes of here. Okay, so these random variables are kind of it's a little bit of a complicated concept to define, right? And I've struggled with it, with actually defining it here. But these are really the key notational thing that is going to allow us to talk really easily about these probabilistic concepts, because we're going to be able to take expected values of these. Okay, and we're not going to take expected values until the next lecture. Hopefully you've kind of seen this before, but we'll talk about expected values and other things like those in the following lecture. Yeah, question.
So if you roll 2 dice, could you save that into one random variable?
Sure, yeah. This is the cool thing about random variables. I can have a random variable for the first die, a random variable for the second die, and a third random variable, right? So I can have random variable die 1, die 2, and then D, which is equal to die 1 plus die 2. Okay, this is die 1 and die 2 are the outcomes of these dice, and maybe I assign values 1, 2, 3, 4, 5, 6 to them, right, based on some probability. I can then say D is then the outcome, right? There's a random process that I rolled 2 dice, the outcome is the face of this 2 die, right? And then the value assigned is the sum of the values on the faces, right? That still fits under this definition here, right? So random variables are really cool. I can do things like I can add them together. We're going to be doing a lot of, it turns out adding together random variables is going to be super important, and we will derive why we're going to be doing this in fact. Okay, so these random variables are going to allow us to do things like add things that we don't know and talk about events and accumulate things together. You can divide, multiply them. And so these will allow us to talk about these random events without actually kind of observing them or think about the potential outcome of certain things. Right, great. Okay, so, yep, okay, and okay, the next thing I want to cover is going to be kind of conditional probability and so independence. This will be kind of the last thing I cover in this lecture before the quiz opens. Okay, so I'm going to think now about having two events. So the reason typically in a probability course you don't define all this at once, but I'm trying to kind of and there's ends up being a lot of repetition because you define everything for events, and you define it again for random variables, and I'm going to kind of go through them in parallel. But let me start with two events, A and B, okay? And I want to talk about the conditional probability of these events. And so the conditional probability, I would say probability of A, so given B, and this is pronounced, I would say probably of A given B or conditioned on B being true, which is conditioned on B being true. Okay, so that's what this conditional probability means. If I roll 2 die, I rolled the first die, I got a 3, and maybe the first die corresponds with with B. So I rolled 2 die, and the first one was a 3. The first B was the event that that the first die is odd, right? And then I roll if I then roll the second die, right, and I want to know the probability that A is odd, right? That the second die is odd. That might be A given B. In that case, it's still going to be 1/2 probability that's odd. Okay, but I could do something more complicated. I could say that B, and so now I only have the case that I have 1 die, or so I've got 1 dice. B is the event that the die is even, okay, and A is going to be the event that the dice, no, the die is the singular. All right. Okay, the A is that the die value is less than or equal to 3. Okay, so now if I know that the dice is even, right, so then this means that it's either 2, 4, or 6, and these are all equally likely, then the probability that's less than or equal to 3. Well, if I didn't know B, then that would be probability 1/2, right? But if I know that the value is even, then this could be 1, 2, or 3. But I know that the values are either 2, 4, or 6. So then I have the probability of A equals 1/2, but the probability of A given that I know B is true is now only going to be equal to 1/3. Okay, because I only have, I know it's restricted to these events. Okay. Okay, so in fact, you can define the probability A given B as the probability of A intersect B. So that means both A and B are true, divided by the probability of B. Okay, so now I can also say the probability of B is equal to 1/2, right? I have 2, 4, 6, they could all be true. And the probability that they both are true, A intersect of A and B, right? That means it has to be the only way to do this intersection, right? This intersection is only 2 is the only thing that's in the intersection, right? So the probability that they're both true, that's going to be 1/6. There's only one thing that can happen when they're both true, divided by 1/2, the probability of B, right? And this is equal to 1/3. So this is, the common definition. Okay. All right. And then an important concept, which we will use, we'll use over the next few weeks, and then you'll see that it is inherently baked into almost all formulations used inside of data analysis, is the concept of independence. Okay, and that is that this is true when the probability of A given B is equal to the probability of A. Okay, so this was the first example I didn't write up here. Yeah, so I can look here. Is the probability of A equal to the probability of A so conditioned on B? Is that true in this example here with the 1 die? That's not true, right? It's 1/2 versus 1/3. Those are not equal in this example. The previous example where I had 2 die and I looked at the first die was even, the second die was even. Yeah, the fact the first die was even did not affect the probability that the second die is also even, if you work that out. So then these would be independent of each other. One event does not influence the probability of the other event. Yeah.
So isn't that the probability of B given A? It was just flipped up. It'll be probability of B intersect A over probability of A.
Yes. Okay, so correct. So that is not the same. Probability of A given B and probability of B given A. This is not equal to the probability of B given A. When we get to Bayes' rule, we're gonna stare this in the face, in fact, because we're gonna want to work with probability B given A, and we're gonna only have access to probability of A given B. And there's a bunch of cases where this occurs, and we'll figure out how to get from here to here. That's what Bayes' rule is going to be all about. Yeah. Yeah. Okay. Yeah. So A intersect B. These are the events that A is true and B is true, right? Okay. A is true when I get value less than or equal to 3. So those are the events. A is true is 1, 2, or 3. B is true, right? If it's even, that's 2, 4, and 6. So if I roll a 1, A is true but not B, right? If I roll a 3, A is true but not B. If I roll a 4, B is true but not A. The only case when A and B are both true is going to be the value 2. So 2 out of, and that's one event, one possible sample outcome out of the 6 possible sample outcomes. If they're equally likely, then that's going to be 1/6, right? The intersection is the intersection of these two sets. Set intersection is defined as the objects, the elements of the sets where they are contained in both of the sets. And 2, 4, and 6 intersect with 1, 2, 3 is only 2. Yeah. Okay. Yep.
Suppose that we have the definition for independence of A and B. Is there any situation where A given B to equal, probability of A given B to equal the probability of A, but it's not true the other way.
So
A is
so
independent
so
B,
A is independent of B. No, if this is true, this is also true. And also, you also get probability of A times probability of B is equal to probability of, should write this larger. You also get probability of A times probability of B equals probability of A conditioned on B. You get all three of these things if you get independence. They're all equivalent to each other. You can actually be a fun exercise after class to work out. So if I start with this equation, I can given this definition of the conditional probability, and I know this is true, I can derive this equation. And I can also derive this equation over here. Right? So I can basically you multiply by the probability of B and you expand, you start here, you expand this to here, I multiply by B, and then you divide through, and you can derive these other equations. So if one is true, the others have to be true as well. Okay.
So is this the rationale for the solution for the Monty Hall problem?
Yeah, so gosh, I love the Monty Hall problem. I forget exactly what's going on there. Those are not independent events, is ultimately what's going on with the Monty Hall problem. So you can think about that through conditional probability.
But this third equation doesn't make sense to me, right? Because if you replace the probability of A given B with the probability of A.
Great, I wrote this incorrectly. Thank you. Good. So this should be probability of A intersect B. Good. So the product of the probability of A and the probability of B should be their intersection. Great. Thank you. Okay. I want to draw a picture here. Again, I like to draw pictures of these sample spaces. And I like to think of, like, I can write an event in the sample space. Think of this as being A, right? So this is the event A. And if I draw event B like this, right, B, right? So now these events drawn this way are going to be, assuming there's uniform probability on the sample space. If you understand what that means, we'll see that next lecture. These are going to be events which are independent of each other in this drawing. Okay. What conditioned, if I write probability of A intersection B, what does that look like? That looks like, well, I'm conditioned on B. So what does that mean? I know B is true. So I know that I'm in this part. This is condition on B true. I know I'm in this part of the sample space. That's what condition on B, how it means in this figure here. Okay, and when I'm conditioned on this being true, well, then I look at the probability of A. Well, the way I've drawn it, A is kind of, I can think of like slicing it up, and for any line, any vertical line I draw in here, the probability of A is kind of proportional to that strip in the height, right? So I could think of this as going from 0 to 1, right? And this is, say, 0.8, and this is, say, 0.4. So then the probability of A based on the area is going to be 0.4, right? That's the difference between 0.8 and 0.4. That's the percentage of its area. And if I restrict to B, So I don't have a full square anymore, but restricted to B, it's still 40% of the area. So the probability is still the same. So these are independent of each other. And if I do it the other way, if I restrict restrict to A being true, then B has a similar property here. If I take the intersection of their probabilities, right? So let's say that the probability of B is like 0.3, then I have that the probability of A equals 0.4, the probability of B equals 0.3, and then I have the probability of A times the probability of B. We know this is 0.12, right? Well, I claim then that is the volume of their intersection. All right, if I were to restrict this, the 0.3 as kind of the width and 0.4 as the height relevant here, I calculate the volume of that rectangle in the middle that intersects the shading of both, and its volume is going to be A intersect B. So they're both true. That's going to be 0.12. They're going to be independent of each other. So this is not always how independence occurs. You don't always get this nice picture, but this picture kind of gives some intuition of what independence is giving you in this case. Okay. Okay, I just want to say one last thing and we'll be done. If I have two random so variables x, y, then they are independent if all events A, which is a subset of the sample space of X, and B, a subset of the sample space of Y, then then I have that the probability of A intersect B is equal to the probability of A times the probability of B. Okay, so to have random variables be independent, I need for all possible events I could consider, they could have the same sample space or different sample spaces, that all possible events have to be independent. Okay, so random variable independence is kind of harder to achieve than events. It's harder to show that random variables are independent just based on construction, but we'll often get this based on some construction or an assumption. Okay, that random variables are independent, and it means a stronger property. So okay, great. I will stop here, and the quiz should be open, so you can start taking the quiz, and I'll be around for questions. It's due by the end of the day, but I suggest you take it now.
That first one, is that
It's a subset.
Yeah.